Hello everyone, welcome to my channel. So I've started offering specialized one-on-one classes in physics, chemistry and math EE for both SL and HL. So for the rates, the standard rate is $35 per hour. If you book like 5 or more classes, it'll be 30, and if you book 10 or more, it'll be 25. So these courses will be tailored to your needs. Whatever you want to learn, we can discuss in these classes. Please don't hesitate to reach out to me. You can contact me at this given email, and yeah, to schedule your class. So with this, let's get started with this paper. Thank you. Hello everyone, welcome back to my channel. Today we'll be solving Chemistry SL Paper 1B of Time Zone 2 of this recent May 2025 attempt. Let's get started with the first question. So yeah, the concentration of calcium ion Ca2 plus in aqueous solution can be determined by titration of ethyl diamine tetraacetic acid EDTA or by atomic absorption spectrometry. EDTA solution must be standardized before use by titrating it with a standard solution of calcium chloride. An accurately weighed mass of powdered calcium carbonate was dissolved in concentrated HCl and heated to remove all of carbon dioxide. And cooling calcium chloride solution was made up to exactly 250 centimeter cube. So what they did here is they put calcium carbonate CaCO3 with HCl. As a result, the byproduct was CaCl2, H2O, and CO2. And they heated it strongly such that all of the CO2 got released from water. Now, first, what would be the most appropriate glassware to make 250 centimeter cube of calcium 2 plus solution? It would be a volumetric flask, right? And you can exactly choose a 250 centimeter cube volumetric flask because this is a standard size, yeah? So it would be 250 centimeter cube volumetric flask. Next, describe the steps involved in preparing the standard solution by dilution of initial calcium chloride solution. Okay. So first, we need to find out the volume of calcium chloride required, the initial volume. Okay. So using this C1V1 equals C2V2 formula, we have to find the volume of the initial calcium chloride solution required. Okay. Then we will use a pipette to transfer that volume to the volumetric flask. Then we need to fill distilled water till we reach the topmost mark. So till the topmost mark, yeah. And last but not the least, we have to shake the solution thoroughly. Okay, done. Next, calcium chloride is not used to make the standard solution because it readily absorbs water. So just how solid calcium chloride could be treated in laboratory to remove all the absorbed water. So what we can do is we can take calcium chloride in a petri dish and we can keep heating it strongly until it reaches a constant mass. Okay. And then what happens is when it's heated up and when it cools down, it'll again absorb water. So we must cool it down in vacuum or inside a desiccator. In that case, it will not absorb any water when it cools down. Okay. So first, CaCl2 must be heated strongly until it attains constant mass. And then cool it down in vacuum or a desiccator. Fine. Next, a sample of tap water was titrated against standard EDTA using Erichrome black tea as an indicator. Fine. So you have the initial burette reading and the final burette readings given. Okay. And yeah, we have to suggest two reasons why the volume added in trial one is much larger uh, yeah, is much larger than the other values because in trial 1 we have approximately added 26.15 centimeter cube of volume. In trial 2 it's 24.25, trial 3 it's 24.30, trial 4 it's 24.20. Okay, so yeah. So there can be two reasons, right? So whenever we are doing titration, the first titration is done roughly. Okay, we let the like burette run until we get the like color change. We approximately get a value, right? And on the next term, we do it slowly to exactly get the like the perfect volume, right? So this could be one of the reasons, right? That first iteration is always done roughly, get an estimate of the endpoint. Yeah. Now, what could be the second, like, what could be another reason? Another reason could be that the initial burette reading is not zero. Okay. Initial burette reading could be like, something like 2 or something like that. Yeah. If the first titration was a rough titration. Okay. So we can say else the initial burette reading mm, must, or instead of must, I can say might have been reported wrong. Or I can also say that the burette could have leaked. Okay, the burette was not like fully stopped, it was leaking liquid, right? So if it was leaking, then yeah, it makes sense. It leaked out 2 centimeter cubes of the liquid. Done. State the name to a value that differs significantly from others, like even from statistic terms, it's outlier. Okay. Suggest a reason why trial 1 should not be included when finding the mean volume of EDTA used. Because trial 1 gives you a huge value, and you know this value is not right. So if you use this value, then the mean value would like come out very high. So that's why we cannot use it. So you can say that the mean volume of EDTA used would come out too high if trial 1 is included. Okay. Calculate the percentage uncertainty in the volume of EDTA used in trial 2. Okay. In trial 2, yeah, there's the initial volume, there's the final volume. If you check, the least count is 0.05. Yeah. You do not say like 20, like 22, like 34.24, 34.28. It's always increment isn't based on like the unit of 5. So here, the final burette reading would be 34.25 plus minus 0.05. Initial burette reading was 10.00 plus minus 0.05. So what happens to the uncertainties? The uncertainties will get added up. So uncertainty will be 0.10 and this will be 24.25. This is the volume. And then the percentage uncertainty, this would be 0.1 divided by 24.25 times 100, which gives you 0.41% approximately. That's the answer to part 4. Mm, okay, now we have 3 more parts and then this question will be done. So it's an absorption and concentration curve. We have to draw the best line of best fit. So sure, we can do this. This line of best fit should pass from the origin. Okay. Yeah. And I'll just make some adjustment. Now this line cannot pass through all the points. So you have to draw it in such a way that it is equidistant from all the points. So approximately like this. Yeah, fine. Next, determine concentration with absorbance 0.9. Absorbance value is 0.9, yeah? So again, you can draw a line at 0. So this is 0.8, 0.82, 0.8488, 0.92961. So 0.09 will be the middle of this line. It will be exactly at the midpoint. And then when you go down, you get this value. Yeah. So this is 8, this is 9. So volume would be, the concentration will be 9.2 ppm. Done. 4 ppm solution was made by diluting 2 centimeter cube solution concentration. So you can use the C1V1 formula. C1V1 equals C2V2, the dilution formula. Concentration 1 would be 4 ppm. So 4.00 ppm. Volume 1. Yeah. 2 centimeter cube, Sox solution to 25 centimeter cube. Okay. This was made using 2 centimeter cube and the final volume is 25. So 25.00 centimeter cube. Okay. This is V1. C2 is what you need to find. V2 would be 2.00 centimeter cube. Now you can do the unit analysis, cancel centimeter cube on both sides. And when you simplify, your answer of C2 would be in ppm, which is 4 times 25 by 2. Gives you 50, yeah? But you have to put 3 significant figures because here you see this has 3, this has 3, this has 4, yeah? So always take the lower significant figures. So answer would be 50.0 ppm. This is the concentration. Done. That's the end of question 1. Moving on to question 2, you have spinach leaves. Where spinach leaves were boiled in water for varying times, the water was cooled and tested for the presence of Fe2 plus ions by titration with standard potassium manganate 7 and KMnO4. Yeah. 3 trials were performed for each boiling time. Each trial, 10 grams of spinach was boiled in a beaker containing 250 centimeter cube of tap water for 5, 10, 15, and 20 minutes. Spinach was then removed by filtration and solution was bottled and stored in a refrigerator until titration was performed. Okay, get it. So the independent and dependent variables. We are changing time, right? So dependent variable is the boiling time or the time. Okay. Now what is the dependent variable? So basically here, like by varying time, we are trying to measure the Fe2 plus concentration. And this Fe2 plus concentration will be measured indirectly, okay, by KMnO4. So dependent variable will be volume of KMnO4 required or volume of KMnO4 added. Done. Now we have to suggest 2 additional experimental conditions that should be controlled to ensure that the methodology for this experiment is valid. Okay. So first, like the water used, it doesn't say distilled water anywhere. So we have to make sure we are using distilled water so that there are no other ions present at the start of the reaction. Yeah. So I can just write like this. Distilled water should be used to ensure no ions are present at the start of the experiment. Now, next, we are using spinach leaves. Now, spinach leaves can vary, right? Some spinach leaves could be greener, some could be dry, okay, some could be like old. Yeah. But here in all the experiments, we should use spinach leaves which are similar to each other. Okay. So I can say spinach leaves should have the same color and freshness. Done. Next, this is the average result. This is the amount of Fe2 plus you found. And like with respect to the boiling time. Yeah. If I state the relationship shown in the graph between Fe2 plus released and the like the boiling time. So we see that the amount of Fe2 plus released, right? The moles of Fe2 plus released does not change, kind of remains the same. You can treat it as an outlier. Okay. So, and say amount of Fe2 plus does not change. Hence, it remains constant with time. Done. We have to comment on range and quality of measurements used in this experiment. Now, in this experiment, you have they have used a very short time frame, right? Just 5, 10, 15, and 20 seconds. So we need more boiling time. What if, it starts giving off more Fe2 plus if you are increasing the boiling time? We haven't checked that, yeah. So you can maybe try boiling it and taking in data for around an hour or 2 hours, and then that would give us a better trend. Yeah. So for the range, we can say we need more time or more boiling time to understand the trend. Okay. And what about the quantity of measurements used in the experiments? Um, Now, thing is, for the measurements, firstly, the measurements have been taken for 5 minutes. Okay. Another thing is they have not taken any measurement at t equals 0. You need the measurement at t equals 0 to understand whether boiling does really make an effect or not. If you see that at t equals 0, before boiling, the amount of Fe2 plus moles is again 0.8. Yeah. In that case, guess what? Boiling doesn't make any, boiling has no effect in this Fe2 plus concentration. So, can say that a measurement at t equals 0 is needed to understand if boiling makes a difference or not. Next, the initial hypothesis was that more Fe2 plus would be extracted from spinach leaves as boiling time increased. Yeah. Evaluate giving a result whether the results support the hypothesis. The result does not support the hypothesis, right? Because there is no increase in the Fe2 plus concentration. The Fe2 plus concentration remains the same. It dipped at 15 minutes. That is probably a human error, but it remains the same. Yeah. So I can say the results do not support the hypothesis as there is no increase in Fe2 plus concentration. So just one modification to the investigation that would make it more suitable for testing the hypothesis. The only modification required is more data points. Okay. We need data points like you're taking data once every 5 minutes. Maybe you can take the data once every 2 minutes. And you have to increase the boiling time. That will give you even more data points. Right. So clearly, you can say more data points should be collected to get a better idea about the trend. Done. Now this would be the last question. Yeah. Reaction of solid sodium hydrogen carbonate with hydrochloric acid was investigated with the same mass of solids, so same mass of NaHCO3, constant volume of different concentrations of acid. Data logger was used to measure the mass of the reaction mixture and all. The results were graphed. Determined by annotating the graph the initial rate of release of CO2 with the 1.5 mole per dm cube HCl. This is the 1.5 dm cube HCl, the dotted line. So I can just draw a tangent here. So you can draw it using a ruler, but I'll use technology here. Yeah, this is approximately the tangent at this point, okay, at t equals 0. The tangent at t equals 0 would give you the initial rate of the reaction, okay. Yeah, so initial rate would be equal to negative of slope of tangent. So it'll be minus slope of straight line. The initial point is 9. So 9, so yeah, 9 minus, and we can take this point because it exactly passes. Okay. So 9 is the like 9 minus 4.8 divided by at 9 the x coordinate is 0, at 4.8 the x coordinate is 2. Okay. When we simplify this, we'll get the answer as 2.1. The numerator is in gram, denominator is in seconds, so unit will be gram per seconds. So 2.1 gram per second would be the answer. Next, determine the average release of CO2 with 0.15 mole per dm cube HCl for the first 20 seconds. So 0.5, this is the graph, so it is the initial case. At 20 seconds, this would be the final case. Okay. Initially, I know at t equals 0, mass would be, this is 9 and then 2 blocks up, so 9.4 grams. Okay. At t equals 20 seconds, we have to find the mass. Okay. So if you check here, this thing is kind of the midpoint of a, midpoint in between 8 and 8.2, this point. Yeah. So as it's in the midpoint, I can just take it as 8.1, which is an approximation, not the exact value. So we can take this 8.1 grams. Okay. Average weight would be negative 9.4 minus 8.1 divided by 0 minus 20. If you put it in a calculator, you'll get 0.065 gram per second. That's the answer. Now the last part, suggest with a reason whether NaHCO3 or HCl was the limiting reactant in the reaction using 0.1 and 1 mole per dm cube. Now see, we know that NaHCO3 is a solid and it has the same mass in both the reactions. Yeah. A limiting reactant will actually it will tell you how much product will be formed. The amount of product formed will definitely come from the mass or the concentration of the limiting reactant. Yeah. So if something is a limiting reactant, what happens is like if you change the mass or the concentration of the limiting reactant, your products will change. Yeah. So between 0.5, 0.5 and 1 mole, right? You're only changing the concentration of HCl. You're doing nothing to NaHCO3. But you see, like more CO2 will be produced. Yep, because mass of reactant mixture decreases. That means CO2 has been produced. So HCl is judging how much CO2 will be produced. So HCl is the limiting reactant. Okay. So limiting reactant will be HCl. And the reason would be NaCO3 has the fixed mass or has the same mass. But the amount of CO2 produced is different, which is only possible if HCl is the limiting reactant. Because we are only changing the concentration of HCl. Done. That's it with this paper. Thank you so much for watching this video. I'll see you all in the next one. Bye-bye.